Here's an example of a problem involving half-life of a radioactive substance. We have a problem where we have an initial amount of radon-222 and a continuous decay rate. So the continuous rate and the word decay is telling us that our formula for the amount of radon is going to be given by this continuous growth formula. Notice that because we're decaying at 17.3%, we have a negative growth rate. And so to be more precise, that really should say 200 e to the minus 0.173 t. If we want to be completely accurate, there's no reason to round that off. So this is the amount of the substance that we have, where the 200 that's sitting in front, this 200 is coming from the initial amount. So the definition of half-life is it's the amount of time it takes for the initial amount to decay to half the initial amount. So I have to do a little bit of arithmetic to know that half of 200 is 100, but this is the problem we're trying to solve. I want to find the t, the amount of time it takes for the amount of this material that we have to be equal to 100, where the initial amount was 200. So that's what we mean by half-life. It goes from, we find it when the amount is half of what it started with. So this gives us an exponential equation that's almost in the form we need to solve it. Our first step would be to get the exponential part. So this piece right here, we'd like to get that by itself on one side. And so I can do that by dividing both sides by 200. So then I have e to the minus 0.173t is equal to 1/2. Notice that it doesn't really matter how much material we're starting with. If the amount of material I start with is here and half of that amount is here, then when I do this first step, I'm always going to have this equation. I'll have the exponential part equal to 1/2. So half-life is the same regardless of how much material you start with. Now to solve this, I'm just going to change this into a logarithmic equation. So it'll be an equation with log base e, and log base e is ln. So I have an equation with the logarithm of the same base, and the only thing that's going to happen is the role of the input and the output are going to swap. So I'm going to have 1/2 is the input for the log, and negative 0.173t is the output for the log. Once I have it in that form, then I'm just going to divide both sides by negative 0.173t, and I'll have log of 1/2 over negative 0.173 is the exact value of t. And then I can put that in my calculator if I want to get, and that would be the right answer if I just wanted the most exact answer. That would be fine. In some of the MyOpenMath problems, it allows you to enter the answer just like that, and then we don't even have to get a calculator out. But if we want to know about how long that is, we could estimate with our calculator. If I put that in my calculator, I get approximately 4.01, and it'll be days. Notice that the unit here is days, and it all goes back to the fact that rate of decay was given as 17.3% per day. So the unit for time through the whole problem will be days. So it takes about 4 days for this material to decay to half the amount you start with, and that will be true regardless of the actual amount that you start with.